All right. So hello everybody. Yes, and then before starting, so I just got a mail from Peter Vincent. So he's on his way with a taxi. So should get the talk. So my name is Haefele. I'm from Maison de la Simulation. I'm working currently on the code Metalwalls. So I will talk about it a bit. But then we got support from many people. So Gabriel Osru from GenC helped us to make the OpenMP implementation, and I'm also part of the GenC technical survey group, and I'm also part of ECHO. I'm managing also the ECHO project. So the idea of this work is, so the objective I'm trying to reach here with this code is to try to evaluate to compare how the different architecture behaves with one production code. Okay, so then originally the code was pure MPI, working only on Xeon. Then we went to Xeon Phi and we made an implementation with OpenACC on GPU. And so basically the same things are parallelized on all the different. At least we did our best on the three platform, and so such that we can compare and from so restitution time, but also energy. And so I will try to show you the first thing. So I will start by the end by presenting the results in a something quite new way. So yes, that's the first time I present this, so feedbacks are welcome. The idea is to have to present the results this way, so to have the energy in the x-axis, so energy required to make the run, and in y-axis the performance, so meaning the number of picoseconds I could simulate per seconds of runtime. Okay, so higher is better, and so lower energy is better. So okay, so we try to push our points top left. Yeah, top left is the best in this thing. Then how a perfect scalability looks like in this plot. Basically that's a vertical line, because if you consider running on n resources, so these resources are running and using p watts in terms of power. So I have t second of execution time. So let's say, so then I have e kilojoule that are required to do my job. Now if I double the number of resources and I assume that my code scales perfectly and the machine scales perfectly in energy, so the machine will use 2p watts at each time. As it scales perfectly, my restitution time is divided by 2, so the energy is the same. And so that should get this vertical line. Basically that's how it looks like. And in general, so then as the world is not perfect, so our code will go to the right, so go away from this vertical line. So I have some data on three systems basically. On the PCP system here at CNEST, so based on KNL. So I made some technical stuff, so just for reference. So here the deployment is with 17 MPI ranks per node and 8 threads per rank. So here I'm using hyper-threading, so two threads per core. So the Broadwell system also at CNES here. So now it's 4 MPI ranks per node and 14 threads, so also SMT2. And so a system at Tidris, GPU based, so open power system. So where it's basically so it's 4 rank per node, and 1 rank can use 1 GPU. That's how it's deployed. So let's have a look at the results. So results is for these three machines with intra-node. So how the code scales inside the node. Okay, so that's going to the top left. So we have super linear scalability. So that looks great, but that's wrong, in fact. The thing is that, for example, if we take the GPU curve, with 1 GPU, you have to pay the system of the whole node in terms of energy. Okay, you have all the memory bus, everything is fired up. even if you use only one single GPU. It means that you will use a lot of energy. If you use two GPU, you will use a little bit more energy, but you will cut in half your restitution time. That's why you get a super linear scaling here. Anyway, you see that in terms of performance, GPUs are much better than, so then that's a full node on KNL and the full node of Broadwell. So in my case, so the KNL is faster, so you have better performance with the KNL system than the Broadwell one. Unfortunately, so oxygen is not that reliable in terms of energy measurement, so I have still large error bars on the energy on the Broadwell. So that's something that should be improved in the future. So yes, that's basically what I said. So that the thing is that so dark silicon, so meaning I don't use some part of the node in order to save energy. If you only just not deploy thread there, it's not enough. Basically, you are still burning a lot of energy. So letting resources idle within a node makes no sense from an energy point of view. That's the bottom line of intra-node scalability here. Now, if we're using several nodes, so here I push the scalability of the code up to when the parallel efficiency reach 75% typically. So I don't go beyond. So I put the code up to the maximum of the scalability. So here you see the KNL, so goes quite straight away, and here we are at 75% of parallel efficiency. So I stop. With the GPU, it doesn't scale with up to 2 nodes. So with one node with 4 GPUs on it, then I'm at maximum. So the code doesn't scale anymore. But you have by far the best results in both energy and performance. So I have exactly the opposite conclusion as compared to Herbert. So here GPUs in my case performs better than KNL. So I have very strange results with the Broadwell in terms of energy. So that's why I put large bars. So okay, energy cannot be trusted here. Still, in terms of performance, still makes sense. Code scale up to 11 nodes on Broadwell, and then is faster than on the GPU. Basically, that's how it's. That's the conclusion here. Right. So okay, that's just some figures. If we take from the performance point of view, at scalability limits, if you consider that Broadwell is the best, then KNL reached 62% of this and GPU 48% of this. From the energy point of view, okay, so Broadwell, you cannot trust, unfortunately, the data. If GPU is 1, then KNL needs 2.5 more energy than the GPU.
How do you measure the energy?
So, that's you fight.
Do you include fabric? Do you include the fact that you have you use fabric?
Yep. So on Slurm, so on the PCP machine here in KNL, I used the BEO tool that Franz presented this morning, and I used the complete node, so including the complete job, including the switches. And you have similar tools on the OpenPower system, where you have you even have the details on if you want to follow how much your memory interface or PCI Express is using as energy. You can follow this as well, and that's how I got these numbers. But yes, I'm kind of the first one who are interested in the numbers. So yes, I was in intense discussion with people here at CNES and with Nicolas Tallet from IBM to make this work. So yes, I finished my slides this morning, basically. Okay. Okay, that was for the results. Okay, how do you get there? So first, Metalwalls. So just in a nutshell, that's a classical molecular dynamics code. Okay, it was developed by Paul Mallon initially. Now it's Mathieu Salan, collaborator at Maison de la Simulation. So he's at EPMC, but he has he's working with that at Maison de la Simulation. Originally it was a pure MPI Fortran code. And yes, so that's molecular dynamics. You have lots of large packages around that are able to do this. This one is a bit particular because he is able to simulate a system with a constant potential electrodes. So I'll come back to this. Polarization effects is not done currently. So that's the kind of system we are simulating. That's supercapacitors. That's energy storage devices. So basically you have ionic liquid, so that the red and the green balls are here, so represented at the molecular level. And then you have two electrodes, so here that are carbons, so nanoporous carbons. And you put a potential, so a difference of potential on the different electrode, and then you study how the matter behaves at the interface, because that's the kind of thing that are very hard to measure for experimentally. That's why they explore it numerically, and they are quite advanced in this kind of field. Yeah, so this constant potential stuff is able to simulate realistic electrochemical systems. So I don't go into the detail. It's easier to look at the computer science point of view. So basically, you have an initialization phase, and then you run for a large number of time steps in production. So typically 10,000. Then you have a first part. So the white box, the blue box, sorry, are the part of the code that are not parallelized. It's quite small in terms of runtime, but still it's serial. And then you have a conjugate gradient that try to find to minimize the charges on the electrode. And then once you have the charge on the electrode, you can compute the forces. If you have the forces, you can push the atom. Then you modify the velocities, and then you loop like this. Okay. So code is quite small. Still, it's really production code. In total, it's 20,000 lines. Yep.
99% is the amount of code, or is the runtime?
No, runtime. It's amount of time.
Parallel or in sequential?
In sequential. In sequential, yeah. And so really, the part you have to work from HPC point of view are basically 7,000 lines. So that's something that is still quite small. That's why I could try to play around with trying to port it. So yes, let's have a look at source code. What do you have to do on the source code to implement this and to be able to run on these new platforms? So I took one kernel. That's not the most complex one, but not the trivial one still. So basically, we are working in Fourier space here. So, and we are 3D. So we have a number of modes in X, Y, and Z. So, and for each mode, we are looping over all our atoms. Okay, we are building a quantity Q that is valid for each of our atom. That depends on something related to the mode and something related to the atom we are treating right now. Okay. I simplify a lot, so you have much more computation, of course, you can imagine, but okay, that's just to get the picture. And then once you have this, you compute the quantity of interest, so that's the quantity where you want to minimize, by having this this calculation. So you reuse it, and then you have a computation of integral. And basically, one of the first things that we had to do to go from Xeon to KNL was a cache blocking, because this, guys, is quite large. That's typically several tens of thousands even. So it means that when you finish to compute this quantity, the beginning of this array is already back in memory, and then you fetch it again back from memory here. Okay, so then you keep, at each mode, then you keep traveling data back and forth from the memory. So cache blocking consists in not working on all atoms at once, but only on part of the atom. So E start, I end, doing this loop such that this guy stays in the cache. Okay, and then this, so you have you add some chunks that you work chunk by chunk, but then the two loops, right? So we are still serial here. To go from MPI, you do not loop over all the modes, but then each rank computes the contribution on the TG pot, but only on a part of the modes. And then you have all reduce here to gather all the results from all the rank. So that's how you get your MPI implementation. And then OpenMP. So that's quite trivial here. So you just have less rank in MPI, and then you put threads, and each thread take care of a different chunk, and then you're done. That's quite okay. And OpenACC, that's a bit more complicated. Putting the parallel here was not enough work for the GPU. It was not enough threads to spawn. So here you have to collapse these three loops. So you have a parallel section here. You have so then you distribute these guys over the gangs by collapsing these three loops. And yes, you can. It's hard to put ky beg of L here. The compiler doesn't like it. So you go for all the modes, and then all the modes that should not be taken in care by this process, then you just cycle here, and that's something that works quite well on the GPU. And then you have a loop vector here. The inner loop is then vectorized, and then with an atomic update to make the reduction on the CG pot. Basically, that's how it works. So at the end of the day, we have an MPI plus OpenMP version that works on Xeon and Xeon Phi, okay, with different deployments in terms of number of tasks and number of threads. MPI plus OpenACC that works on open power system typically. In the end, if we compare to the very first version of Metalwalls when I start my activity on it, so we have accelerated by a factor of 3.6. So that's quite nice. And the thing is that now we have all this within one code base. So very few parts of the code have to be with define, and so we still have. So we have lots of pragmas everywhere, yes, but okay. So that's sometimes a bit painful to read, but at least, yeah, we don't have if-def all over the code. That's quite nice. And yes, I would like to stress the point that this code is quite heavily used. So in 2016, it has used 28 million CPU hours. And so at that time, it was only 2.5 increase in performance, but then it would have required 70 million CPU hours to do the same experiment. So that's 40 million CPU hours saved. That's, yeah, basically 1 million euros. So that's worth optimizing code. So the next step are the following. So basically, so this rattle algorithm that is still serial, we would like to put it in parallel, such as to push the scalability a bit. I think we have to communicate a lot, so I think we will not scale that far, but okay, still improving. So we are currently working on data flow engine, so that's FPGA implementation. So with my colleague, I'm quite excited by that. For now, that's the current activity we are having. We are almost done. At least it works in the simulator. Now we want to really run it on a real chip. And something that could be interesting to look at is mixed precision computation. So in order to put some parts of the code that are now in double precision back to single precision, in order to win a factor of 2. Yes, so from the energy point of view, yes, would like to improve the precision of energy measurement on Xeon processor. I would be quite interested to run on the Italian system. So this David system was built by E4. Apparently, they worked on a careful integration of the same element of open power, so meaning power 8 GPU Pascal plus NVLink, but with a special care on energy efficiency. So maybe more than IBM, so would be really happy to compare these two. And yeah, once we have our DF implementation, there is a machine that will be available at Jülich that will embed this DFE, so this FPGA. I'm really happy to look at how it works. Yep, and so last slide about some thoughts, more to trigger discussions tonight with a glass of wine. Some facts that for now we are the largest supercomputing system are already limited by energy. They have to fit into this energy budget of 20 megawatts. We are still in Moore's law regime with the doubling transistor every 18 months, but that's getting longer and longer. And at some point we'll stop, so we will have a fixed transistor budget, okay, at some point. And then the question boils down to, okay, how do you organize the transistor you have? How do you build a programming model that are able to build application that will run on this new organized transistors, and of course with the software stack? And my current experience with DFE programming is quite interesting in the sense that, so that's a completely different world where you don't have any more instructions. Okay, it's not a processor, it's FPGA, it's logic that you can program, and what you have to describe is a electronic circuit. So you describe how the data flows from memory to inside to the memory and so on. So you describe how the data flows, how the data moves. And that's what costs time and energy. So I think it's quite relevant. Even I think that's thing that we have to keep in mind, that could lead us to new architectures that could be interesting from both performance and energy. Yep. Thank you.